In situ state of stress. In many cases, it is essential to know the in situ stresses and pore pressures conditions prior to altering the situation by the construction of a facility. The response of the soil and this behavior of the structure is tightly tied to the conditions prior to construction. For example, in the case of a retaining wall, the pressure on the wall is very tightly tied to what were the horizontal stresses in the ground prior to making the excavation for the wall. And time again, we will see that we need to start with a known stress state in the ground to do a certain type of an analysis. But fundamentally also, the properties of the soil are related to the stress state. The soil stiffness, for example, Young's modulus, is a function of the stress state in the ground. The higher the stress, the stiffer the soil. The lower the stress, the softer the soil. So if we want to relate the soil properties to stress state, we must start with a known stress state in the ground. Now, unfortunately, sometimes establishing the in situ stress state is the greatest uncertainty in an analysis. The greatest uncertainty lies in the lateral or horizontal earth stresses. It is the sigma x stresses that are the most difficult to establish accurately. That is the K0 conditions. The vertical stress is related to the overburden and is relatively easy to assess, but it is the lateral or horizontal stresses that are related to K0 that are the most difficult to establish with any degree of certainty. The reason for this is that in situ stresses are a reflection of the self-weight or gravity. That's quite easy to handle, but the in situ stresses are also related to the geologic history. That is the past loading and unloading, and this component of the memory of the soil is rather difficult to establish sometimes, although we can approximate it. In a finite element analysis, we can do what is called a gravity turn-on or a gravity activation type of analysis. And in this type of analysis, in essence, the self-weight of each element is converted into downward vertical forces at the nodes of each element. Now, it is rather curious that in the real life, of course, gravity always acts, but in a finite element model, we activate the gravity after the model has been built. In this sense, an in situ analysis is very much analogous to a centrifuge test, where the model is first built and then the gravity is applied through the rotation in a centrifuge. So it's useful to think of in situ analysis as being analogous to a centrifuge test where we activate the gravity after the model has been built. This concept can also be used effectively in certain other situations, as we will see throughout these sessions. So sigma W has a special analysis type. The analysis type we will select is in situ. And so when we select the in situ analysis type, then we are in essence attempting to establish the state of stress in the ground, and sigma W has a special algorithm to do this. Now generally, when you do an in situ type of an analysis, the general behavior is like this. The vertical stress, sigma Y, is controlled by the unit weight of the soil. The lateral stress, or the sigma x, is controlled by one of two things. It's either controlled by Poisson's ratio or with a specified K0. And when you do an in situ analysis using sigma W, the computed stresses are independent of the specified soil stiffness E. So E does not come into play when we establish the in situ stresses using this analysis type. Now, very simply, it is easy to establish the state of stress in the ground when we have a horizontal ground surface. The reason this is relatively simple is because the shear stress in the XY plane is 0. So the shear stress in the XY plane is 0. As a consequence, we can establish the vertical and the horizontal stresses at a particular point, and sigma y, or vertical, is simply equal to the unit weight of the soil times some distance h. It's the overburden stress. And sigma horizontal, or sigma x, is equal to the vertical stress times some ratio K0, but as we will see in the next slide, when we use K0, then we need to deal with effective stresses. So the key here is that tau xy is 0 when we have horizontal ground surface. And we can make use of this in computing the stresses in the ground for K0, high K0 conditions, and that is because this is 0. So, effective in situ stresses, we of course know that the vertical stress effective stress is the vertical total minus the pore pressure. The horizontal effective is equal to the vertical effective times K0. Then the horizontal total is equal to the horizontal effective plus Poisson's ratio. And we have to go through this procedure all the time because we cannot say this expression here. We cannot say that the total horizontal stress is equal to the total vertical stress times K0 minus Poisson's ratio. This results in the wrong total stresses. This results particularly in the wrong horizontal stress. We cannot do this, and so we have to go through this procedure here in order to get at the correct horizontal stress. So as I've already noted, we can control the horizontal stress by either specifying a Poisson's ratio, and when we specify a Poisson's ratio, we compute K0 from this equation which we just talked about a few minutes ago. The disadvantage of using the Poisson's ratio to control K0 is that the maximum allowable is a K0 of 0.98. Theoretically, we cannot have a Poisson's greater than 0.5, and it creates numerical difficulties as we approach a Poisson's ratio of 0.5. So sigma W limits the specification of Poisson's ratio to 0.495, which represents a K0 of 0.98. The advantage of using Poisson's ratio is that we can establish the stress state in any irregular ground or sloping ground surface. It does not have to be a horizontal ground surface, so that is the advantage. So even if we have sloping ground, we can make an estimate of the in situ stress state by using the Poisson's ratio approach. Now sometimes we need to specify conditions or K0 conditions where K0 is greater than or equal to 1, and sigma W allows us to specify K0, and specifying K0 greater than equal to 1 or greater, but theoretically this is only applicable to horizontal ground conditions. The advantage is that this is suitable for any K0 conditions provided the ground surface is horizontal. And when the ground surface is horizontal, the XY shear stress is equal to 0. The disadvantage is that it's not directly suitable for sloping ground conditions. If we were to indeed have a high K0 conditions and we want to model sloping ground conditions, we would have to start with horizontal ground conditions and then make an excavation to remove this soil, and then we would have the starting condition for a slope with high K0 conditions. So let us move on then to an exercise using sigma W. We will open the file sig01 in situ analysis and illustrate how we establish in situ stress state conditions for when we have a K0 of a half. K0 of a half using Poisson's ratio. Then we will create a second analysis where we have a specified K0 of 2. A K0 of 2, so that we can do easy hand calculation, spot checks with hand calculations. We're going to use a unit weight of 20 kilonewtons per meter cubed, and you will see that in this file the unit weight of water has been set to an approximate 10 kilonewtons per meter cubed. This is again for convenience with checking with hand calculations. And we'll look at a situation where the water table is 2 meters below the ground surface. So what we want to then do is to create stress profiles with depth for the total vertical stress, total horizontal stress, effective vertical stress, effective horizontal stress, and pore water pressures, and then to do spot checks with hand calculations at the base of the profile. So let's go then to GeoStudio. And open up the file SIG01. File, open. Sigma SIG01. The problem has been sketched for you. We need to create materials, apply the material, define the pore pressure conditions using a water table, apply the correct boundary conditions, and then do the in situ analysis. To begin with then, under the icon Key in Analyses, notice that we have an analysis type, and we have selected the in situ analysis from the drop-down list. So we are doing an in situ analysis here. In this particular case, we are asked, where does the initial pore water pressure conditions come from? In this case here, we will select that the initial pore water pressure conditions come from a water table. The pore water pressures come from a water table. So we are going to start with one analysis where we use a specified Poisson's ratio. Key in materials. We add a new material. Let's call this the native soil. And in this particular case, we want to say something about pore pressures, but we do not have any change in pore pressure due to loading, so we can use the effective drained parameters for this type of an analysis. It's the effective drain types of parameters because we want to say something about the pore pressures during the calculations. Effective drain parameters, we're going to use a linear elastic model, is more than adequate, and as I noted earlier, the Young's modulus does not come into play in the in situ analysis, so any approximate value is adequate for an in situ analysis. We said that the unit weight of the water was 20 kilonewtons per meter cubed, and that we were going to use a Poisson's ratio of 1/2. Notice that we selected 5,000 kPa for Young's modulus. The unit weight is 20 kilonewtons per meter cubed. And when we specify Poisson's ratio as 1/3, then we compute here what the equivalent K0 is. And notice that when we use a Poisson's ratio of 1/3, we get K0 equal to 0.5. So in this case, we are not going to specify an in situ K0. We will use Poisson's ratio to control K0. Recall that K0 is equal to Poisson's ratio divided by 1 minus Poisson's ratio. So if Poisson's ratio is equal to 1/3 divided by 1 minus 1/3 is equal to 1/3 divided by 2/3 is equal to 1/2 is equal to 0.5. So we have specified a Poisson's ratio of 1/3, which gives us a K0 condition of 0.5. So we have defined our material. Now we can say draw materials, and we will apply the material to a region. Secondly, we said that the initial pore water pressure comes from a water table. Turning on our snap to grid, we can say draw initial water table, and we will just accept the default for the negative pressure head and draw our water table at 2 meters below the ground surface. We now need to apply boundary conditions, draw boundary conditions. We want rollers, so to speak, on the ends such that we are free to move in the vertical direction but not in the horizontal direction. And in this sense, this is analogous to a constrained loading test, and that we are making the strain in the x direction 0, and then we need to fix the problem at the base, fixing both x and y at the base of the problem. At this stage, we can check on our Verify Optimize icon, and it's saying that there is sufficient information provided to make some calculations. We can click on our Solve icon, save the problem, and click on Start. And now go to our results view. By default, we are contouring Y total stresses. We can apply some contour labels. Clearly, it's if the font is too small for the labels for the contours, we can increase the font size for the labels. The fact that the vertical stress contours are horizontal is an indication that the stress is uniform all across this section. Now, the most useful way of looking at the computed in situ stresses is by graphing the stresses along a vertical profile. Going to draw a graph. We'll add a graph, and first of all, let us graph the pore water pressure, with the distance y. We have selected pore water pressure, and we have selected y. Now we need to set the location. Where do we want the graph created? And we will select a geometry item. And the reason for this line down the middle is so that we could conveniently look at a profile in the center of the section. Clicking on Show Graph. Here is our graph of pore water pressure distribution with depth. And it's easier to look at the graph if we rotate the graph such that y is on the vertical axis. And we should name this graph pore pressure. And as we can see here, that here is the specified water table where the pore pressure is 0. It's negative above the water table and positive below the water table. This distance is 8 meters, so therefore 8 times the unit weight of the water is equal to 80, which is the pore pressure at the base of the profile. So that is correct. Now let us add another graph and say total vertical stress. We go to the total stress category, selecting Y total stress, again plotting it against Y and setting the location once again on the line down the center of the section. We can show the graph, once again rotating the graph such that we get Y on the vertical axis. So now we have the total vertical stress. We can now clone this graph, say clone, and we will make a total horizontal stress graph. And all we now need to do is to select X total stress. cloning the total vertical again, say clone, but this time we want the effective vertical. The effective vertical stress, and now we need to go to the effective stress group here. The effective stress group, selecting Y effective stress, and so that is a graph of the vertical effective stress. Finally, we need to make another plot saying clone. We want the effective horizontal stress. The same group, we simply select X effective. So now we have our group of graphs, and first of all, the total vertical stress. Clearly, the total distance is 10 meters. So we have a depth of 10 meters. We said that the unit weight of the soil is 20 kilonewtons per meter cubed. Therefore, we should have 200 at the bottom. So that is correct. Now, we can look at the effective vertical, and the effective vertical should be equal to the total minus the pore pressure. So when we hold down the control key, we can plot pore pressure at the same time, and we can plot the total vertical at the same time. So we already established that the pore pressure is 80, the total is 200, therefore sigma V effective is equal to 200 minus 80 is equal to 120, and therefore, if we have done everything correct, sigma horizontal effective should be equal to 120 times 0.5 should be equal to 60. And if we now plot the effective vertical and the effective horizontal, we indeed see that, as we had just calculated by hand, the effective horizontal is 60 kPa. Now, one other thing that is worth noting is that the total sigma W is formulated in such a way that the total stress is always 0 at the surface. And so it is an important concept inherent in sigma W in situ analysis that the total stress in both the vertical and horizontal direction is 0 at the ground surface. Now, one last point, which is always the last check, and that is that in order to ensure that we have established the correct horizontal total stress, we recall that we said that the effective stress, sigma X effective, was equal to 60, and the pore pressure is equal to 80. Therefore, sigma X total is equal to 60 plus 80 is equal to 140, which is what sigma W has computed. The point that needs to be checked most often is to ensure that we have obtained the correct total horizontal stress. Returning then to the define view, clicking on the Key in Analyses icon, we want to now do a second analysis where we specify a K0. The analysis will be very similar, so we can clone the current analysis. Let's call this analysis number 2, specified K0. And now to analyze this case, we need to create a new material. Key in Materials, selecting the current native material. We can clone this material such that everything is more or less the same. So let's say specified K0. And in this particular case, what we will do is we are going to check this box, specified in situ K0. And we can now specify a K0 of 2. We have a new soil then, specifying the in situ K0 as 2. We are in the second analysis. We can then say draw materials and selecting the specified K0, applying it to these sections, and we can then quickly reanalyze for another high K0 condition. Going then to the results view, returning to the draw graph command. Once again, we have our pore pressure distribution with depth. The total vertical stress is the same as before. The effective vertical is 200 minus 80 is 120 at the base. So we have 200 minus 80 equals 120, which is 120. That is the effective vertical stress at the base of the problem. So we have the effective vertical is equal to 120. Therefore, the effective horizontal is 120 times K0 is equal to 120 times 2 is equal to 240. This is the horizontal effective stress. Therefore, the horizontal total stress must be equal to the horizontal effective stress plus the pore pressure is equal to 240 plus 80 is equal to 320. So to check first then, we check the effective horizontal is 240, which we just got from 120 plus 120 times 2 is 240, and then finally the total horizontal stress, we just computed the fact that the total horizontal stress at the base of the section should be 320, which indeed it is. It is 320. This then shows the procedures that are available in sigma W to establish in situ stresses. We can control K naught with specifying a Poisson's ratio, or we can control K naught by a specified K naught. Once again, specifying K naught is useful when K naught is 1 or greater. Specifying the horizontal stresses through a Poisson's ratio is useful when K naught is less than 1. It is always good practice to make these graphs of the stress distribution with depth and to do spot hand calculations to ensure that the in situ stresses have been established correctly. Particularly you should spot check the total horizontal stress in the section to ensure that it has been computed and is correct. This brings us to the end on showing you how to do in situ type of analysis in sigma W.